Hello class. This is going to be one of two lectures. I'm going to break it up on section 5.3. Enthalpy. It's enthalpy, as you already know from the laboratory lecture, is essentially what we call heat that comes from a process at constant pressure. So that's what we're going to be working towards. We've got a lot of definitions to get through to get there, and enthalpy was defined in order to be precise. Thermochemistry is accounting for the energy of chemistry, and it's just like accounting. It requires a lot of definitions and a lot of sign conventions that what goes in, what goes out, etc. So thermochemistry is a branch of chemical thermodynamics, the science that deals with the relationships between heat, work, and other forms of energy. Substances act as reservoirs of energy, meaning that energy can be added to them or removed from them. Energy is stored in substances. It can be kinetic energy and it can be chemical energy in the form of bonds. That's why I crossed it out. The total of all possible kinds of energy present in a substance is called its internal energy. Sometimes people represent energy with E. We're going to use U. I think it's a German thing. The relationships between the change in the internal energy, delta U, by the way, delta always means change, heat, Q, and work, W, is summarized in the first law of thermodynamics, that the change in the internal energy is equal to the heat plus the work. Now, if you have a system, delta always means the final minus the initial, and if heat flows out of the system and work is done by the system, you notice that the value is going to be negative because U is going to be smaller in the final state than it was initially. It has lost it to heat and work. So whenever heat or work flows out of a system, they are negative quantities. Energy can be transported into a system, resulting in an increase in internal energy. The system absorbs heat from the surroundings, and Q is positive, or the surroundings do work on the system, or W is positive. Energy can be transferred out of a system, resulting in a decrease in internal energy. The system releases heat to the surroundings, and Q is negative, or the system does work on the surroundings, W is negative. And it's just showing Q in, Q out, W in. There's already a typo there. Q in, W in, and W out. Oh, work on the system, that's what they mean, and work by the system. So the internal energy of a system can be changed by heat flow and work. If heat flows into the system, Q in, or work is done on the system, that is Q on, its internal energy increases, and delta U is greater than 0. If heat flows out of the system or work is done by the system, its internal energy decreases and delta U is less than 0. A type of work called expansion work or pressure volume work occurs when a system pushes back on the surroundings against a restraining pressure. The surroundings compress the system. Okay, that's when the surroundings are doing work on the system, and this is when it is indeed expanding against the outside pressure. Consider an internal combustion engine. We're just going over everything, but the most important thing about this slide is it's beginning to define the word exothermic. That is, Q is negative, or we'll later find that delta H is negative for the reaction. And that defines an exothermic reaction, that it is releasing heat to the environment. And also in the internal combustion engine, work is being done on the environment as well. So we're going to skip over this. The whole, the state function thing is important to scientists, but it's not important to you at this time. It just says that we had to create a variable that depended only on the states involved. And this is that variable, enthalpy. Enthalpy is defined as the sum of a system's internal energy and the product of the pressure and the volume. So H is equal to U plus PV. Enthalpy values for specific substances cannot be measured directly. Only enthalpy changes for chemical or physical processes can be determined. Commonly, so we're going to set up a system for determining delta H of reactions, and although in principle each chemical would have an absolute an absolute H value, we'll never know it. The whole system is based on delta H's, and as you know, we're going to be dealing with delta H of formation. So anyway, commonly chemical and physical processes occur at constant pressure. At constant pressure, the enthalpy change is, the pressure is constant, so it's P delta V. And work is minus P delta V. And so delta H is equal to delta U, which is Q plus W, and minus the PV, but in this case that P is going to be minus PV of the work. Anyway, turns out that under constant pressure situations that delta H is equivalent to the heat released by a system. And that's what most of chemistry deals with, is experiments on the bench and a constant pressure situation. There is a situation which is not at constant pressure, and that's reactions that occur in a bomb calorimeter. The volume of the system is kept constant, and its pressure goes up. And we have a way of dealing with that too, but it's not in this chapter, so let's move on. Chemists usually perform experiments in open containers under normal atmospheric conditions, so the external pressure is constant. At these conditions, only the work done is caused by the expansion or contraction, and then the heat flow and the enthalpy change for the process are equal. This makes enthalpy the most convenient choice for determining heat. Well, we're saying it makes the most convenient choice, but it certainly, I don't think it's been proven, but it happens to be a convenient choice. Chemists use a thermochemical equation to represent the changes in both matter and energy. In a thermochemical equation, the enthalpy change is written to the right of the balanced equation. This delta H value indicates the amount of heat associated with the reaction as written. If the direction of a chemical equation is reversed, the arithmetic sign of delta H is also reversed. A process that is exothermic in one direction is endothermic in the opposite direction. So exothermic means releases heat, and endothermic means absorbs heat. So we've got the burning of hydrogen in oxygen to yield water. It releases heat, but the breaking of water into hydrogen and oxygen absorbs heat. If the coefficients of the chemical equation are multiplied by some factor, the enthalpy change must also be multiplied by that same factor. Okay, so meaning that delta H is an extensive property. So if we have this reaction, if we increase everything by a factor of 2, so too do you need to increase the delta H, or by a factor of a half, so too you need to reduce delta H by a factor of 1/2. Delta H of a reaction depends on the physical state of the reactants and products, and so these must be shown. We're going to go to the tables, and the tables will have the hydrogen in the gaseous state, and oxygen in the gaseous state, and water in the liquid state. For example, if gaseous water is formed instead of liquid water, we end up with a different value here. Sucrose is C12H22O11. When sucrose reacts with potassium chlorate, 43 kilojoules of heat is produced. And so what they're going to want you to do in this case is determine what the energy for this reaction is as written. So what you have to do is determine what the limiting reagent is. In this case, it's potassium perchlorate, and then scale this with respect to the moles of potassium perchlorate, and then determine how much energy there is given the 8 moles of potassium perchlorate involved in this reaction. That's what they do here. And that ends up being the answer. Enthalpy changes are typically tabulated for reactions in which both the reactants and products are at the same conditions. The standard state. Okay, it acknowledges here that 1 bar is the standard pressure for the thermodynamics tables. 1 molar concentration is the standard concentration for the thermodynamic tables. And something they did not put on this slide, but it's on the next slide, is that 25 degrees C is the standard state. The ideal gas law had STP, standard temperature and pressure, which was 1 atmosphere and 0 degrees Celsius, or 273 degrees Kelvin. And for the thermodynamic tables, they've chosen a different set of standards. And on top of that, you've got 1 molar concentration thrown in there as well, as if we're talking about something that's a solute. That's the reason why all the quantities given in these tables have a little O at the top of them. That little O means standard states. So we will include a superscript O in the enthalpy change to symbol to designate standard state conditions. Now there are ways of taking these values away from the standard state, and that's beyond the scope of this course. But the numbers from the tables will always be with a superscript 0. The standard temperature is 25 C or 298 K, laboratory temperature. The symbol delta H0 is used to indicate an enthalpy change for a process occurring under these conditions. The enthalpy changes for many types of chemical and physical processes are available in the reference literature, which will be Appendix G of our text. Recall that delta H is an extensive property. It is proportional to the amount of substances involved. And delta H is normalized to a often delta H is normalized to a per mole basis. And that's what you get out of the tables. Now the tables, not those tables, the tables deal with the reaction of the formation reaction of each of these compounds. And I think we're going to stop at this point and continue this in another lecture. Thank you. Escape. Boom. And